All right, in the last video we learned how cell diagrams work and how that relates to voltaic cells and how we actually get any useful information out of that and how to write it all out. In this video we're going to kind of learn how to use that to calculate voltage. Okay, so here's the thing. The voltage of a cell is based off the difference in potential energy between the two electrodes. But there's no specific reason that any of those has to have a specific value. So somebody along the way decided that this reaction and this should be aqueous. Okay, that this reaction is going to be set equal to 0. And we're going to do this at standard conditions, so anything that's a gas, we assume 1 atmosphere, anything that's a solution, we assume 1 mole, standard conditions. Oh, room temperature, okay. So, somebody along the way arbitrarily decided this should be 0. Well, some reactions that we're gonna see are have values above this, and some have values below this. So some of them are negative, some of them are positive. All we care about is the difference. I wanna talk about this reaction for a minute, because this looks weird. Really, like you have an acidic solution and you have hydrogen gas. I don't know, it doesn't seem like it should be obvious that that would even be a voltaic cell. So it turns out that here's what it looks like. What you end up having is a wire connected to a platinum electrode. Again, it's a solution that doesn't have any solids in it. Like neither of these is a solid to make a good electrode, so platinum, okay? And then what you do is you have this sitting in some sort of container, like a test tube or something, okay? And in this, we are going to have a tube that has hydrogen gas being pumped in at 1 atmosphere of pressure. So the gas is being pumped downward. Okay, because there's nowhere else for it to go. Okay, and in here we have a solution of 1 molar acid, H+. Okay, and the idea is that what happens is the solution level is right here, and as this stuff pushes down, it forms bubbles. So basically it bubbles hydrogen out. And so right at this surface where you have hydrogen gas pushing down and a solution of H+, and it's all in contact with the platinum, in theory, there could be electrons exchanged, and this is a wire that would connect to another half reaction. It's kind of weird looking. Not what I would pick as my standard value, but because it seems super difficult to like set that one up, but you know, having the bubbles around the platinum in an acidic solution is good enough, apparently. Okay. So this is called, this is all standard electrode potential. Okay, standard reduction potential, it's all kind of the same concept. Okay, so this is considered the standard electrode. Its value is set to 0. Okay. Well, what we need to look at is how do we use this to actually calculate anything? Okay. So I am going to place this table on course. You guys can print it off. Please print it off. Please have a copy of this, because I don't know how to tell you to do this without this information. Please don't memorize this. I stole it from a textbook and they called it table 19.1. Yeah, I don't know. So we're gonna go with that. So using table 19.1, what we do is we can use this to calculate standard electrode potential. So it's at standard conditions, so everything's either 1 atmosphere or 1 molar, which is not a big deal. Standard electrode potential is essentially, Ecell at standard conditions. Okay, we just need to know how to connect it, or how to do this. Here's the thing though. Some reactions need to be oxidation and some need to be reduction. These are all written in the form of reduction. Okay, which means the cathode side, which is the reduction side, is going to be written in the correct order. The anode side will actually need to be reversed and the sign will need to be changed. Okay, so let me write some of that down here. So it's a big long list of half reactions written in the form of reductions. Okay, and each half reaction has a cell potential. Okay, and literally it's not that difficult. You take the right minus the left is essentially the gist here. So E sub cell, you take the cathode, which is already written in the correct direction, right? We said cathodes are the reduction side. These are all written as reduction. Minus the anode, which is the one that needed to be reversed anyway. Oops, I can't write legibly today, sorry. Sorry for all the scribbling outs here. But essentially, this is the right side of the cell minus the left side of the cell, or of the entire cell diagram. That's the entire concept. Okay, so if we had this cell diagram, which is the one we've already kind of seen over and over and over again, but that's okay. Okay, what we would do is we would look up, so an example, what we would do is we'd look these things up. We need the half reaction where zinc goes to zinc 2 plus. Well, this is the one that's going to be written the wrong way, so we need to find zinc 2 plus and zinc, which I don't know how well you guys can see this on here, but if you print it off, you'll be able to find it. Okay, zinc 2 plus 2 electrons form zinc. This is written in the opposite order that we're used to, but that's okay. It says its value is negative 0.76. And the units on this are volts. Okay. Then we need to look up the copper one. So if we look around, there's copper 2 plus forming copper 1 plus, but that's not what we have. We have copper 2 plus forming copper solid. So if we go up a little farther, we have copper 2 plus 2 electrons forming copper solid. And this has a value of positive 0.34. So literally to do this calculation, you just take this number minus that number. Okay, so it's minus a negative, so the value comes out to positive 1.10 volts. Okay, not too bad. This chart is a little weird. Like obviously some of these have very complicated balanced equations, but it still works out to be the same thing. Okay, there's really nothing too unusual about that. Okay. All right, I guess we'll stop there for this one. All right, thank you.